Hello everyone, my name's Alex Hahn, and today we're going to be looking at the thermodynamic property of entropy. So what is entropy? Entropy is a thermodynamic property that can often be extremely difficult to understand or visualize. So today we're going to try to help you guys understand that a little bit better. I'd like to start with a simple example to illustrate this concept. If I take an ice cube from the freezer and place it on my counter, it will begin to melt. When the ice cube came out of the freezer, its molecules were set in place with a very little energy in a rigid lattice structure. However, when the ice cube begins to melt, its molecules are released from this structure and become more random as the ice turns to water. If I were to evaporate this water into a gas, its molecules would become even more dispersed and random. A simple diagram of molecules in ice, water, and water vapor shows this pretty easily. Watch as the ice melts, the molecules become more and more dispersed and clearly have higher energy states than they did in their lattice structure. So what happened to the ice cube's entropy? A simple way to think of the results in this experiment is that the disorder in the system increased as the ice melted, and therefore its entropy increased. Although disorder is a decent way to think of the thermodynamic property of entropy, it can often be misleading. Let's think of the ice cube example in terms of energy. What caused the ice cube to melt and its molecules to reach a higher energy state? In order for the ice cube and the surroundings to be at equilibrium, the surroundings added heat to the ice cube until the water was at the same temperature as the surroundings. This spontaneous process allowed the ice cube to melt and its molecules to have more energy. Therefore, the ice cube's molecules have more possible combinations of energy states and locations they can be. This allows us to arrive at a better definition of entropy. Entropy is a measure of the possible ways energy can be distributed in a system. Now that we have a better conceptual understanding of what entropy is, let's get a little more technical and look at a more complex example. The second law of thermodynamics explains that the entropy change of any spontaneous process is equal to the entropy change of the system plus the entropy change of the surroundings, and that value must be greater or equal to 0. A spontaneous process is simply one that will occur without any interaction with the system. This is known as the increase of entropy principle. This means that during any spontaneous process, like the ice cube, the entropy change of the universe must increase. Let's use a simple experiment to illustrate this concept. For the experiment, you will need 2 metal blocks, a stovetop, and an oven mitt. Using your stovetop, heat one of the metal blocks until it is red hot. Using safety precautions, touch the heated block to the room temperature block and allow them to sit in contact for a few minutes. Once they are safe to touch, feel the 2 blocks. What do you notice? They have reached equilibrium with each other, and they are now the same temperature. Now, let's think of what happened in this example in terms of entropy. To do so, let's look at the diagram of a simplified version of our experiment, with 4 molecules in both the hot bar and 4 in the cold bar. For our example, we are going to quantize our molecules' energy levels in order to arrive at a conclusion. Let's say that in the hot bar, 3 molecules have a 1 energy level, 1 molecule has a 2 energy level, represented by the motion lines. The cold bar has 3 0 energy levels and 1 1 energy level. If we defined entropy as the possible ways energy can be distributed in a system, we can use simple math to determine the possible ways the hot and cold bar's molecules can be arranged. The cold bar has 4 different possible states, and the hot bar has 56 to begin with. Now, when we put the 2 bars in contact, they reached equilibrium with each other, as we saw in the experiment. They evenly distributed their energy over the 2 metal bars. Now, there are a total of 3 energy quantizations on each bar. Using some simple math again, we are able to see that each bar now has a total of 20 possible energy arrangements. Using Boltzmann's equation, the change of energy is equal to Boltzmann's constant times the natural log of the ratio of final possible arrangements over original possible arrangements. As you can see, when we calculate the values for both the systems and the surroundings and add them up, their values add up to above 0, so the increase of entropy principle is confirmed. Although we used very simple examples today to illustrate the concept of entropy and the second law of thermodynamics, I hope you gained a better understanding of the fundamentals of entropy. As we showed, although measure of disorder is often used to define entropy, a better approach is using the total possible distributions of energy over a system. Using our experiment, we also proved the second law of thermodynamics as well as the increase of entropy principle. This concept is one of the most important truths in all of thermodynamics and can be applied not only in a lab, but also in everyday life.